The moon is only 3 days away. Mars is 6 months. We've had the technology to go for decades, so why haven't we? Because NASA discovered something after Apollo that changed everything, and it's hidden in plain sight, written in the physics of space itself. Today we will explore what's really stopping us from going beyond the moon. If you're fascinated by humanity's journey beyond Earth and the challenges that await us among the stars, make sure to hit that subscribe button and give this video a like. Now let's get started. When the Apollo astronauts journeyed to the moon, they were exposed to something Earthbound humans rarely encounter: the full, unfiltered fury of space radiation. But here's what most people don't realize. Those missions lasted 8 to 12 days. That's it. 8 days of cosmic exposure, and they got lucky. The sun was relatively calm during those missions. No major solar storms. No catastrophic radiation bursts. Just a quick sprint to the moon and back before the universe could remind them how fragile flesh and blood really are. Going beyond the moon? That's a completely different game. We're not talking about a week-long excursion anymore. A mission to Mars, our nearest planetary neighbor and humanity's next giant leap, would take at least 6 to 9 months just to get there. Then you'd need to stay on the Martian surface for another 1.5 years, waiting for the planets to align properly for your return journey. Add another 6 to 9 months for the trip home, and you're looking at roughly 900 days minimum. That's more than 2.5 years away from Earth's magnetic shield, floating through an ocean of radiation that wants to tear apart your DNA. Molecule by molecule, cell by cell. Let me paint you a picture of what space radiation actually is, because this isn't like the radiation you might associate with X-rays or even nuclear power plants. This is something far more ancient and far more powerful. Out there, beyond our planet's protective magnetic bubble, two main types of radiation dominate the cosmic landscape. First, there's galactic cosmic radiation, or GCR for short. These are particles, mostly protons and atomic nuclei, that have been accelerated to nearly the speed of light by supernova explosions, collapsed stars, and other violent cosmic events happening billions of miles away. Some of these particles have been traveling through the universe for millions of years before they happen to intersect with a human body. And when they do, they don't just bounce off. These particles are so energetic, so fast, that they slice through spacecraft hulls, through spacesuits, through skin, through bone, and deep into your cells, shattering DNA strands and creating cascades of secondary radiation as they go. The really terrifying part? There's no escaping them. They come from every direction, all the time, like an invisible cosmic rainstorm that never stops. On Earth, our planet's magnetosphere deflects most of these particles, and our thick atmosphere absorbs what gets through. We're shielded by billions of tons of air and a magnetic field generated by a churning iron core. But in deep space, you're naked, exposed, vulnerable. Then there's the second threat: solar particle events, or SPEs. These are sudden explosive bursts of radiation from our own sun. When the sun has a particularly violent outburst, a coronal mass ejection, or a solar flare, it can hurl billions of tons of charged particles into space at speeds exceeding 1,000,000 miles per hour. If astronauts are caught in one of these storms without adequate protection, the radiation dose can be lethal within hours. Not years, not months, hours. During the Apollo era, NASA got incredibly fortunate. Mission planners timed the launches between solar maximum periods when the sun is most active, but even then, astronauts were one major solar storm away from catastrophe. In fact, between the Apollo 16 and Apollo 17 missions, a massive solar event erupted that would have delivered a deadly radiation dose to anyone caught on the lunar surface or in transit. The timing was pure luck. We dodged a bullet we didn't even know was coming. Today we understand these risks far better. Research conducted aboard the International Space Station, combined with data from radiation monitoring experiments like RADMON developed through collaboration between the European Space Agency and CERN, has given us unprecedented insight into what astronauts actually face beyond low Earth orbit. The ISS orbits within Earth's magnetosphere, so it still receives significant protection, but even there, astronauts experience radiation levels 10 times higher than what we get on Earth's surface. Multiply that exposure for a Mars mission. Remove the magnetosphere's protection entirely, and you begin to understand the scope of the problem. Scientists estimate that astronauts on a round-trip Mars mission could receive a cumulative radiation dose equivalent to getting a full-body CT scan every 5 to 6 days for nearly 3 years straight. The long-term health consequences are sobering. Increased cancer risk, cardiovascular damage, cataracts, central nervous system effects that could impair cognitive function, memory, and decision-making. And here's the kicker. We don't have perfect data on what those doses will do over time because no human has ever been exposed to that much cosmic radiation. We're extrapolating from studies on cancer patients who received radiation therapy, from survivors of Hiroshima and Nagasaki, from astronauts on shorter missions. But a Mars journey? That's uncharted biological territory. Now, you might be thinking, can't we just build better shielding? Wrap the spacecraft in thick metal walls or water tanks? Use lead? The problem is, physics itself fights back against us. Traditional shielding materials like aluminum, which spacecraft are typically made from, do block some radiation. But when high-energy cosmic rays slam into those atoms, they create secondary radiation through a process called spallation. It's like trying to stop a bullet with a sheet of glass. Sure, the glass might slow it down, but now you've got glass shards flying everywhere, potentially causing even more damage. Water and hydrogen-rich materials offer better protection because they can absorb and scatter radiation more effectively without generating as many dangerous secondary particles. Some mission concepts propose surrounding crew habitats with water storage tanks, essentially using the water you need to survive as a radiation shield. Others suggest using polyethylene or other hydrogen-rich plastics. NASA's Orion spacecraft, designed for deep space missions including the upcoming Artemis program, incorporates some of these advanced materials. But here's the brutal reality. To provide truly adequate shielding for a multi-year Mars mission, you'd need walls several meters thick. The mass required would be astronomical, and every kilogram you add to a spacecraft costs tens of thousands of dollars to launch. You'd need so much shielding that the mission becomes economically and practically impossible with current rocket technology. And speaking of Mars, this brings me to a point you'll find deeply relevant. The challenges of radiation exposure don't just affect the journey, they fundamentally shape what happens when humans finally arrive on the Martian surface. If you think the trip is dangerous, wait until you hear about what life on Mars actually entails. The red planet has no global magnetic field, only a wisp of an atmosphere, meaning anyone living there would face constant radiation bombardment. This creates a cascading series of problems that go far beyond what we're discussing today. In fact, I've covered this extensively in another video exploring why the first humans on Mars will be trapped there forever. The radiation challenges we're talking about now are just the beginning of a much darker reality for Mars colonization. I'll leave the link in the description and pinned on the comments. So radiation is our first massive barrier. But it's not the only one. Not even close. Let's talk about something that sounds almost poetic but is actually a nightmare. The human body eating itself in zero gravity. We evolved under the constant pull of Earth's gravity. Every system in your body, from your cardiovascular network to your bones, from your muscles to your inner ear, developed over millions of years with the expectation that gravity would always be there, pressing down, providing resistance, forcing your body to work. Remove that force, and the human body doesn't just adapt, it degrades rapidly. Astronauts aboard the International Space Station lose approximately 1 to 2% of their bone mass every month they spend in microgravity. Read that again. 1 to 2% per month. That's 10 to 20 times faster than the bone loss experienced by elderly people with osteoporosis here on Earth. Your bones literally dissolve, leaching calcium into your bloodstream, which then gets filtered out by your kidneys. This creates a double problem: weakened skeletal structure and an increased risk of kidney stones from all that excess calcium floating around. But it gets worse. Muscles atrophy at a similarly alarming rate. Even with the 2 to 3 hours of intense daily exercise that ISS astronauts are required to perform, they still experience significant muscle loss, particularly in the legs, back, and core. Imagine spending 9 months in transit to Mars, followed by a year and a half on a planet with only 38% of Earth's gravity, and then another 9-month journey home. By the time you return to Earth, Your legs might not be able to support your own body weight. Your spine could have weakened to the point where standing upright is agonizing or even dangerous. Then there's your heart. In microgravity, your cardiovascular system doesn't have to work as hard to pump blood throughout your body. No gravity means no blood pooling in your legs. Sounds convenient, right? Except your heart is a muscle, and like any muscle that isn't challenged, it weakens. Your heart literally shrinks. Studies have shown that astronaut hearts become more spherical in shape and lose muscle mass during long-duration spaceflight. When these astronauts return to Earth and gravity reasserts its pull, their weakened hearts struggle to pump blood effectively, leading to dizziness, fainting, and dangerous drops in blood pressure. Your eyes suffer too. Without gravity to regulate fluid distribution, bodily fluids shift upward toward your head. This causes facial puffiness, sinus congestion, and more seriously, increased intracranial pressure. This pressure can flatten the back of the eyeball, changing its shape and causing vision problems. Some astronauts have experienced permanent vision changes after long-duration missions. We call this condition spaceflight-associated neuroocular syndrome, and we still don't fully understand how to prevent it or reverse it. Let me give you some perspective here. The longest any human has continuously spent in space is 437 days. That record was set by Russian cosmonaut Valery Polyakov aboard the Mir space station in the mid-90s. When he returned to Earth, despite rigorous exercise protocols throughout his mission, he still required weeks of rehabilitation before he could walk normally again. His mission was entirely within low Earth orbit, still partially protected by Earth's magnetosphere, with the knowledge that Earth and rescue were always just a few hours away if something went catastrophically wrong. Now imagine doubling that duration. Imagine being not just hours from Earth, but months away. Imagine knowing that if something goes medically wrong, if your bone density drops too far, if your cardiovascular system starts failing, if your cognitive function begins to decline from radiation damage, there's no coming home early, no emergency abort. You're committed to the journey, millions of miles from any hospital, any doctor beyond your crewmates, any hope of rescue. The psychological weight of that isolation is itself another challenge entirely. And that brings us to the mental and psychological gauntlet that deep space explorers will have to endure. Humans are social creatures. We evolved in tribes and communities surrounded by the sights, sounds, and smells of a living planet. We need variety. We need nature. We need space to move and explore. A Mars mission confines you to a capsule roughly the size of a small RV for the better part of 3 years, with the same handful of people, breathing recycled air, eating reconstituted food, with no fresh water beyond what you can recycle from your own sweat and urine, and absolutely no possibility of stepping outside without a spacesuit. The isolation factor alone is staggering. Previous isolation studies conducted in simulated Mars habitats here on Earth, like the HIC's project in Hawaii or Russia's Mars 500 experiment, have documented serious psychological strain even in carefully selected, highly trained individuals. Depression, interpersonal conflict, decreased motivation, and cognitive decline all emerge when humans are confined to small spaces with limited external stimulation for extended periods. And those experiments had one critical difference from an actual Mars mission. The participants knew they could quit. They knew that Earth, with all its beauty and chaos, was right outside the door. Real Mars astronauts won't have that luxury. The psychological pressure of knowing you cannot leave, that you are trapped in a tin can hurtling through the void, could push even the most mentally resilient individuals to their breaking point. There's also the issue of communication delay. On the ISS, astronauts can have real-time conversations with mission control and their families. There's essentially no delay. But Mars? At its closest approach to Earth, light takes about 3 minutes to travel between the two planets. At its farthest, that delay stretches to 22 minutes. That means a simple back-and-forth conversation could take nearly an hour. Imagine experiencing a medical emergency, a critical system failure, or a mental health crisis, and having to wait up to 44 minutes for a response from the only people who might be able to help you. You are, in every practical sense, alone. The Apollo astronauts, despite being 250,000 miles from Earth, could still communicate with mission control with barely noticeable lag. They could look up and see Earth, the beautiful blue sphere hanging in the black, always visible, always there. a constant reminder that home was just a few days away. Mars astronauts will watch Earth shrink to a pale blue dot indistinguishable from the stars, and eventually they won't be able to see it at all without a telescope. That level of isolation, that severance from everything familiar, from everyone you've ever known, has never been tested in human history. Now let's talk about something that sounds mundane, but is actually one of the most complex engineering challenges we face: life support. On Earth, nature handles life support for free. Plants produce oxygen. The water cycle purifies and redistributes water. Ecosystems break down waste and recycle nutrients. It's a self-sustaining system refined over billions of years. In space, we have to artificially replicate all of that, and we have to do it perfectly, because even a small failure can be fatal. The International Space Station maintains life support for 6 or 7 astronauts, but it's not a closed system. It relies on regular resupply missions from Earth, cargo ships arriving every few months carrying fresh water, food, spare parts, and breathable air. If a critical component fails, a replacement can be launched within weeks. For a Mars mission, none of that infrastructure exists. You can't call for a resupply. You can't order replacement parts. Everything you need for survival has to be either carried with you from the beginning or manufactured using local resources once you arrive. Current life support technology can recycle about 93% of water aboard the ISS through filtration and purification systems that convert urine, sweat, and even moisture from exhaled breath back into drinkable water. That sounds impressive until you realize that 7% loss means you still need regular water resupply. On a multi-year Mars mission, even a small percentage of loss compounds over time. You'd either need to carry impossibly large reserves or achieve near-perfect recycling efficiency, something we haven't yet demonstrated. Oxygen production faces similar challenges. The ISS generates oxygen through electrolysis, splitting water molecules into hydrogen, and oxygen using electricity from solar panels. But solar power becomes less effective the farther you travel from the Sun. Mars receives only about 43% of the solar energy that Earth does, which means solar panels are less efficient. You need more panels, more mass, more complexity. Alternative power sources like nuclear reactors offer solutions, but introduce their own risks and engineering hurdles. Then there's food. Astronauts aboard the ISS eat pre-packaged, preserved meals shipped from Earth. For a Mars mission lasting nearly 3 years, you'd need to carry approximately 11,000 kilograms of food per person, and that's assuming you're consuming around 2,000 calories per day with no waste. The mass alone is prohibitive. This is why NASA and other space agencies are investing heavily in developing hydroponic and aeroponic food production systems that could grow fresh vegetables in space. But growing food requires water, light, nutrients, and careful environmental control. It adds layers of complexity and potential failure points to an already incredibly complex mission. Every system I've described, radiation shielding, life support, power generation, food production, has to work flawlessly for years without fail. There's no room for error. One malfunctioning valve, one contaminated water filter, one failed circuit board could cascade into a mission-ending catastrophe. And we're talking about technology that has to function in an environment of extreme temperature fluctuations, vacuum, radiation exposure, and microgravity, all while being light enough to launch and robust enough to survive years of operation without maintenance. It's an engineering puzzle of almost incomprehensible difficulty. But let's step back for a moment and ask a deeper question. Why does all of this matter? Why should we care about going to Mars or beyond when we have so many problems here on Earth? This is where the perspective shifts, where the narrative becomes not just about survival, but about what it means to be human. We are the universe trying to understand itself. Every atom in your body was forged in the core of a dying star billions of years ago. The iron in your blood, the calcium in your bones, the oxygen you breathe right now, all of it was created in stellar furnaces that lived, burned, and exploded long before our solar system even existed. We are literally made of stardust. And something extraordinary happened on this small blue world orbiting an unremarkable yellow star in the outer reaches of the Milky Way galaxy. Matter became aware. The universe opened its eyes and began asking questions. Why are we here? Where did we come from? Are we alone? These aren't just philosophical questions, they're scientific ones, and the only way to answer them is to explore. For millions of years, our ancestors looked up at the night sky and wondered what those points of light were. They told stories about them, built calendars around them, navigated by them. Eventually, we built telescopes and discovered that the universe is far larger, far older, and far stranger than anyone imagined. We found that those stars are other suns, that many of them host their own planets, and that the cosmos is teeming with worlds beyond counting. But telescopes can only tell us so much. At some point, if we want real answers, we have to go there. We have to send our eyes, our hands, our minds into those distant places and see them up close. That's what exploration is. That's what we do as a species. It's written into our DNA. This restless curiosity, this need to see what's over the next hill, across the next ocean, beyond the next horizon. The moon was humanity's first step beyond our cradle. Between 1969 and 1972, 12 humans walked on another world. They looked back at Earth from 250,000 miles away and saw our planet in a way no generation before them ever could. That shift in perspective, that image of Earth as a fragile blue marble suspended in infinite darkness, changed us. It gave birth to the environmental movement. It reminded us that borders are human constructs, that we all share one planet, one atmosphere, one fate. Going to the moon wasn't just about planting flags and winning a Cold War competition, it was about expanding the human story. Mars is the next chapter. It's the closest planet where humans might one day build a second home, a backup for our species, a new branch on the tree of human civilization. But getting there requires us to solve problems we've never faced before. And here's the beautiful irony. Solving those problems doesn't just help us explore space. It helps us here on Earth too. The technologies developed for space exploration have given us satellite communication, GPS navigation, weather forecasting, water purification systems, advanced medical imaging, scratch-resistant lenses, memory foam, cordless tools, and thousands of other innovations that we now take for granted. When engineers figure out how to recycle water with near-perfect efficiency for a Mars mission, that technology can provide clean drinking water to communities on Earth that desperately need it. When researchers develop lightweight, radiation-resistant materials for spacecraft, those same materials can improve cancer treatment and nuclear safety. When we learn how to grow food in the harsh conditions of space, we develop resilient agricultural techniques that can feed people in deserts, in drought-stricken regions, in places where traditional farming fails. Space exploration pushes the boundaries of what's possible. It forces us to ask hard questions, to innovate, to collaborate across nations and cultures toward a common goal. And it inspires. When people watched the Apollo 11 moon landing in 1969, children around the world looked up and said, "I want to do that." Those children became the scientists, engineers, doctors, and teachers who built the world we live in today. Inspiration is a resource we often overlook, but it's one of the most powerful forces in human civilization. Now, I want to be very clear about something. I'm not saying space exploration is easy, or that we should ignore problems on Earth in favor of chasing cosmic dreams. What I'm saying is that the challenges of going beyond the moon are real, they are immense, and they reveal fundamental truths about the universe and our place in it. Understanding these challenges teaches us humility. It shows us that nature doesn't care about our ambitions, that the laws of physics apply equally to everyone, and that survival in this universe requires intelligence, cooperation, and adaptability. Right now, as I speak, NASA's Artemis program is preparing to send humans back to the moon for the first time in over 50 years. Artemis 2, the first crewed mission, will carry 4 astronauts on a journey around the moon, testing systems and procedures that will eventually take us to Mars. Just this month, in February 2026, NASA conducted critical wet dress rehearsal tests for the Space Launch System rocket, fueling it with hundreds of thousands of gallons of super-cold liquid hydrogen and liquid oxygen, running through countdown sequences, identifying problems, and fixing them. These tests revealed hydrogen leaks and technical issues that need to be resolved before launch, currently scheduled for no earlier than March 6, 2026. This is how progress happens. One test at a time, one problem solved at a time, one step closer to the next giant leap. The Artemis program isn't just about returning to the moon. It's about building infrastructure, establishing a sustainable human presence in deep space, and learning how to live and work beyond Earth's protection. Artemis 3 will land astronauts near the lunar South Pole, a region we've never explored before, where water ice exists in permanently shadowed craters. That water isn't just scientifically interesting, it's a resource. Water can be split into hydrogen and oxygen for rocket fuel and breathable air. It can support human life. The moon becomes a proving ground, a place where we learn to extract resources, build habitats, and survive in hostile environments before we attempt the far more dangerous journey to Mars. But even with all this preparation, even with decades of research and technological development, the fundamental barriers remain. Radiation will still bombard astronauts with invisible DNA-shredding particles. Microgravity will still deteriorate their bones and muscles. Isolation will still test the limits of human psychology. Life support systems will still need to function perfectly for years without resupply. These aren't problems we can simply throw money at and make disappear. They're challenges rooted in physics, biology, and the nature of space itself. So what are the solutions? How do we actually overcome these barriers? The truth is, there's no single magic bullet. Instead, we're developing a web of interconnected technologies and strategies, each addressing a piece of the puzzle. For radiation protection, researchers are exploring multiple approaches. One involves developing pharmaceutical countermeasures, drugs that could help cells repair DNA damage more effectively or protect against oxidative stress caused by radiation exposure. Studies conducted on the International Space Station and in laboratories here on Earth are testing various compounds, including antioxidants and radioprotective agents, though we're still years away from a proven solution. Another approach involves timing missions to minimize exposure. Solar activity follows an 11-year cycle, fluctuating between solar minimum and solar maximum. Launching during solar minimum reduces the likelihood of encountering massive solar particle events, though it doesn't eliminate the constant background of galactic cosmic radiation. Advanced shielding materials are also under development. NASA has tested vests made of polyethylene embedded with hydrogen-rich compounds that astronauts could wear during solar storms or sleep behind to reduce cumulative exposure. Some mission concepts propose using the spacecraft's water and food supplies as radiation shielding, positioning storage tanks around crew quarters to create a storm shelter where astronauts could retreat during high radiation events. Others are investigating electromagnetic shielding, using powerful magnets to create an artificial magnetic field around the spacecraft, mimicking Earth's magnetosphere. However, generating a field strong enough to deflect cosmic rays requires enormous amounts of energy, and the technology remains experimental and prohibitively heavy for current launch systems. Then, there's the concept of faster propulsion. The longer you spend in deep space, the more radiation exposure you accumulate. If we could cut transit time from 9 months to 3 months, we'd reduce exposure by 2/3. Nuclear thermal propulsion systems, which heat propellant using a nuclear reactor rather than chemical combustion, could potentially achieve this. NASA and private companies are actively developing these technologies, but they introduce new challenges around safety, politics, and engineering complexity. Nobody wants a nuclear reactor exploding during launch or malfunctioning in orbit. For the physiological degradation caused by microgravity, artificial gravity is the most elegant solution. If you've ever seen science fiction movies featuring rotating spacecraft, you've seen the concept. Spin a spacecraft or habitat module fast enough, and centrifugal force simulates gravity. The crew experiences an outward pull that mimics the sensation of weight. This would prevent bone loss, muscle atrophy, cardiovascular deconditioning, and fluid shift problems. The engineering challenge is creating a structure large enough to rotate without causing disorienting Coriolis effects, where different parts of your body experience different gravitational forces. Current concepts involve tethered spacecraft that spin around a central axis or large rotating rings. But these designs are massive, expensive, and unproven. In the absence of artificial gravity, pharmaceutical interventions are being researched. Bisphosphonates, drugs used to treat osteoporosis on Earth, have shown promise in reducing bone loss in astronauts, though they come with potential side effects. Exercise regimens continue to be refined, with resistance training and high-intensity interval protocols showing better results than earlier approaches. But exercise can only do so much. It slows degradation, it doesn't prevent it entirely. For psychological resilience, mission planners are incorporating lessons from extreme isolation studies, Antarctic research stations, submarine crews, and even prison psychology. Careful crew selection becomes critical. You need people who are not only technically competent, but also emotionally stable, adaptable, and capable of functioning under extreme stress. Personality compatibility matters enormously when you're locked in a confined space with the same individuals for years. One interpersonal conflict that spirals out of control could jeopardize an entire mission. Virtual reality technology offers interesting possibilities for psychological support. Imagine being able to put on a headset and virtually walk through a forest, stand on a beach, or visit your hometown, even while you're millions of miles away in a metal capsule. These immersive experiences could provide crucial mental relief, a way to escape the monotony and confinement, if only temporarily. Communication systems are also being improved to reduce the psychological impact of delay. Pre-recorded video messages, asynchronous communication platforms, and even AI companions designed to provide conversational support could help astronauts feel less isolated. But here's something we don't talk about enough: the ethics and philosophy of who gets to go. A Mars mission will be one of the most dangerous endeavors in human history. The people who volunteer for it are accepting a significant possibility that they won't come back. They're risking cancer, organ damage, cognitive decline, and psychological trauma for the sake of exploration. Who do we ask to make that sacrifice? How do we balance the collective human dream of reaching Mars with the individual cost to the people who actually go? Some researchers have proposed that we should send older astronauts, people in their 50s or 60s who have already lived full lives and for whom the long-term cancer risks are less significant. After all, if radiation exposure increases your chance of developing cancer 20 years down the line, that's a different calculation for someone who's 60 versus someone who's 30. But is that ethical? Are we essentially saying that older lives are more expendable? Others argue we should send younger astronauts because they're physically stronger, recover faster, and have the stamina for the grueling demands of the mission. But then we're asking people to sacrifice decades of potential life for a journey into the unknown. There's also the question of reproduction and genetics. Space radiation doesn't just affect the astronauts themselves. It can damage reproductive cells, potentially affecting any children they might have after returning to Earth. We've seen this in animal studies. Mice exposed to simulated space radiation show increased mutations in sperm and eggs. If humans spend years in deep space, will they come back sterile? Will their children face higher rates of genetic disorders? These are questions we don't yet have answers to, and they carry profound implications. Some visionary thinkers have even proposed using genetic engineering to create humans more resistant to radiation, people whose DNA repair mechanisms are enhanced, whose cells are more resilient to oxidative stress. The technology to do this, CRISPR and other gene editing tools, already exists in primitive forms. But the ethical minefield here is staggering. Are we talking about creating a new subspecies of humans designed specifically for space? What happens when those individuals return to Earth? Do they integrate back into society, or are they fundamentally different? Who decides what modifications are acceptable? These questions push us into territory that feels uncomfortably close to eugenics, and they demand careful, thoughtful consideration from scientists, ethicists, policymakers, and society as a whole. Let's zoom out for a moment and look at the bigger picture. All of these challenges, radiation, microgravity, isolation, life support, psychological strain, they're not just obstacles, they're filters. The universe is testing us, asking whether we're truly ready to become a spacefaring species. And here's the profound realization: maybe we're not ready yet. Maybe the fact that going beyond the moon is so incredibly difficult is the universe's way of telling us that we need to grow up first, that we need to develop not just better technology, but better wisdom, better cooperation, better understanding of ourselves and our place in the cosmos. Consider this. The same international collaboration that built the International Space Station, bringing together the United States, Russia, Europe, Japan, and Canada, despite political tensions and ideological differences, is the kind of cooperation we'll need for a successful Mars mission. Space exploration at this level requires resources and expertise beyond what any single nation can provide. It demands that we see ourselves not as competing countries, but as one species with a shared destiny. That's a hard lesson, and we're still learning it. The challenges of deep space exploration also force us to confront our relationship with technology. We're creating increasingly complex systems, artificial environments where every breath of air, every drop of water, every calorie of food is manufactured and controlled. We're building machines that have to function flawlessly for years in the harshest conditions imaginable. This requires a level of engineering precision and systems thinking that pushes the absolute limits of human capability. And when we succeed, when we build a spacecraft that can safely carry humans to Mars and back, we'll have demonstrated mastery over some of the most difficult technical problems ever attempted. But there's a philosophical paradox embedded in all of this. The more capable we become at creating artificial environments, the more dependent we become on technology for survival. On Earth, if every piece of modern technology disappeared tomorrow, humans could still survive. We could hunt, gather, find water, build shelter using nothing but our hands and the natural world around us. Our ancestors did exactly that for hundreds of thousands of years. But on Mars, or in transit through deep space, there is no natural world to fall back on. If your life support fails, you have minutes, maybe hours before you die. There's no backup plan, no wilderness to escape into. You are utterly, completely dependent on the technology keeping you alive. This raises profound questions about resilience and vulnerability. Are we making ourselves stronger by developing these capabilities, or are we creating fragility disguised as strength? What happens if a critical component fails and we lack the materials or knowledge to repair it? What happens if a solar storm damages electronics beyond repair? The pioneers who crossed oceans and continents faced enormous dangers, but they could at least breathe the air and drink the water. Space offers no such mercy. Despite all these challenges, despite the radiation, the physical degradation, the psychological strain, the engineering nightmares, and the ethical dilemmas, we're still moving forward. Why? Because the alternative is stagnation. Because staying on one planet, no matter how beautiful and precious Earth is, leaves us vulnerable to extinction-level events we can't control. Asteroid impacts, supervolcano eruptions, pandemics, climate shifts, solar events, any number of catastrophes could wipe out humanity if we remain confined to one world. Becoming a multi-planet species isn't just an adventure. It's insurance for the survival of consciousness itself, and there's something deeper, something almost spiritual about the drive to explore. We are curious beings. We ask questions. We imagine possibilities. We dream of horizons we've never seen. That quality, that restless yearning to know what lies beyond, is perhaps the most fundamentally human characteristic we possess. It's what drove our ancestors out of Africa to populate every continent on Earth. It's what sent Polynesian navigators across thousands of miles of open ocean using only stars and currents to guide them. It's what compelled explorers to climb the highest mountains and dive to the deepest ocean trenches. And now, it's what calls us to the stars. The universe is vast beyond comprehension. Our Milky Way galaxy alone contains somewhere between 100 billion and 400 billion stars. Most of those stars have planets. That means there are potentially trillions of worlds in our galaxy alone, and there are an estimated 2 trillion galaxies in the observable universe. The sheer scale is overwhelming, humbling, almost incomprehensible. And somewhere out there, in that cosmic ocean, are answers to the biggest questions we've ever asked. How did life begin? Are we alone? What is the ultimate fate of the universe? What are the limits of what's possible? We won't find those answers sitting on Earth. We have to go looking. We have to build the ships, train the crews, solve the impossible problems, and take the risks. That's what exploration is. It's not about having all the answers before you start. It's about being willing to venture into the unknown precisely because you don't know what you'll find. Right now, in 2026, we stand at a threshold. The Artemis program is preparing to return humans to the moon. Private companies like SpaceX are developing massive rockets designed to carry humans to Mars. International space agencies are collaborating on deep space habitats, advanced propulsion systems, and life support technologies. Researchers are studying radiation countermeasures, artificial gravity, and closed-loop ecosystems. We are closer to sending humans beyond the moon than we've been since the 1970s. But let's be honest about the timeline. A crewed Mars mission is still at least a decade away, possibly longer. The challenges we've discussed aren't going to be solved overnight. Each barrier requires years of research, testing, failure, and iteration. We will lose spacecraft. We may lose astronauts. The path forward is paved with risk, uncertainty, and heartbreak, but that's always been true of exploration. The people who first crossed the Bering Strait into the Americas didn't know what they'd find. The sailors who followed Magellan around the world knew most of them wouldn't return. The Apollo astronauts climbed atop rockets fully aware that those rockets might explode. Courage isn't the absence of fear. It's moving forward despite the fear because the goal matters more than the risk. So what's really stopping humans from going beyond the moon? The simple answer is physics, biology, and engineering. The universe has rules, and those rules are unforgiving. Radiation kills. Microgravity degrades. Isolation breaks minds. Distance makes resupply impossible. Life support systems are complex and failure-prone. These are hard physical realities that don't care about our ambitions. But the deeper answer is more nuanced. What's stopping us isn't just the technical obstacles. It's also economics, politics, and priorities. A human mission to Mars will cost hundreds of billions of dollars, require decades of sustained effort, and demand international cooperation on a scale we've rarely achieved. It requires governments and societies to invest in something that won't produce immediate returns, that won't cure diseases next year or solve poverty next month, but that will expand the horizon of what's possible for our species. That's a hard sell in a world facing climate change, economic inequality, political instability, and countless immediate crises demanding attention and resources. And honestly, that criticism is valid. We should be solving problems here on Earth. We should be addressing hunger, disease, environmental destruction, and injustice. But here's the thing. It's not an either-or proposition. The resources spent on space exploration represent a tiny fraction of global spending. NASA's entire annual budget is less than 0.5% of the United States federal budget. The European Space Agency operates on similar proportions. We can pursue space exploration and address earthly problems simultaneously. In fact, I'd argue we must do both. The technologies, the mindset, and the inspiration generated by space exploration help us tackle problems here at home. Climate science relies heavily on satellite data collected by space agencies. Our understanding of Earth's weather systems, ocean currents, ice sheet dynamics, and atmospheric chemistry comes largely from instruments orbiting our planet. The same engineering that designs life support for Mars missions develops water purification and air filtration systems that save lives on Earth. The challenge of growing food in space is teaching us how to grow food in harsh terrestrial environments. The pursuit of distant horizons makes us better at navigating the challenges we face right here, right now. There's also an intangible but crucial element: hope. In a world that often feels dark, divided, and directionless, space exploration offers a vision of humanity at its best. It shows us working together towards something greater than ourselves, pushing boundaries, solving problems, achieving things that seemed impossible. That vision matters. It inspires young people to pursue science and engineering. It reminds us that our differences, as real as they are insignificant compared to what we share. It gives us perspective. The late astronomer Carl Sagan spoke about this beautifully when discussing the pale blue dot photograph That image of Earth taken by Voyager 1 from nearly 4 billion miles away, where our entire world appears as a single pixel of light suspended in a sunbeam. He said that every human who ever lived, every saint and sinner, every king and peasant, every young couple in love, every mother and father, hopeful child, inventor and explorer, every teacher of morals, every corrupt politician, every superstar, every supreme leader, every creator and destroyer of civilization existed on that tiny mote of dust. That perspective, that cosmic humility, is something we desperately need. Going beyond the moon forces us to reckon with our smallness and our significance simultaneously. Yes, we are cosmically insignificant, temporary sparks in an unfathomably vast universe, but we are also extraordinary. We are matter that has become conscious, that has learned to ask questions and seek answers, that has figured out the laws governing reality itself, and use that knowledge to reach for the stars. Both truths coexist, and both are essential to understanding what it means to be human. Now, let me bring this back to the concrete realities. The barriers stopping us from going beyond the moon are being actively addressed by thousands of brilliant people working across dozens of institutions and countries. At NASA's Johnson Space Center in Houston, researchers are testing advanced spacesuits designed to provide better radiation protection and greater mobility. At the European Space Agency's facilities in the Netherlands and Germany, engineers are developing closed-loop life support systems that recycle air and water with unprecedented efficiency. In Russia, cosmonauts continue pushing the boundaries of long-duration spaceflight aboard the International Space Station, providing crucial data on human adaptation to microgravity. Private companies are also joining the effort. SpaceX's Starship, the largest and most powerful rocket ever built, is designed specifically to carry large crews and cargo to Mars. As of February 2026, Starship has completed multiple test flights, each one gathering data and refining systems. Blue Origin is developing lunar landers and orbital habitats. Numerous smaller companies are working on specialized technologies, radiation sensors, food production systems, in situ resource utilization equipment that could extract water and oxygen from lunar or Martian soil. The international collaboration extends beyond traditional space powers. The United Arab Emirates sent the Hope orbiter to Mars in 2020, studying the Martian atmosphere. China landed the Zhurong rover on Mars in 2021 and has ambitious plans for sample return missions and eventual crewed landings. India's space program successfully placed an orbiter around Mars in 2014 and landed near the lunar South Pole in 2023. Japan is developing advanced propulsion systems and participating in the Artemis program. Space exploration is becoming a truly global endeavor, bringing together diverse perspectives, capabilities, and dreams. This collaborative spirit is essential because the challenges ahead aren't just American challenges or Russian challenges or Chinese challenges. They're human challenges. Radiation doesn't discriminate by nationality. Microgravity affects all bodies equally. The psychological strain of isolation is universal. When we finally send humans to Mars, they'll represent all of humanity, carrying with them the dreams and hopes of billions of people from every nation, culture, and background on Earth. But let's not romanticize this too much. Space exploration is hard, dangerous, expensive, and slow. There will be setbacks. There will be tragedies. The path to becoming a multi-planet species is littered with obstacles, and some of those obstacles may prove insurmountable with current technology. We might discover that human biology simply can't withstand deep space radiation exposure without causing unacceptable health consequences. We might find that the psychological toll of isolation is too great, that humans break mentally before they can reach Mars. We might encounter engineering problems we can't solve with the materials and energy systems available to us. Or we might succeed. We might develop medical countermeasures that protect against radiation damage. We might design spacecraft with artificial gravity that keeps astronauts healthy. We might create psychological support systems that help crews maintain mental health across the vast distances of space. We might build life support systems so robust and efficient that they function flawlessly for years. We might prove that humans can not only survive beyond the moon, but thrive there, establishing permanent outposts on the moon, Mars, and eventually the asteroid belt and the moons of Jupiter and Saturn. The honest truth is, we don't know yet which scenario will unfold. We're still in the early stages of figuring this out, but that uncertainty is precisely what makes it worth doing. The greatest achievements in human history have always involved venturing into uncertainty, risking failure, and persevering despite overwhelming odds. We didn't know if we could build cities, develop agriculture, create written language, harness electricity, split the atom, or land on the moon until we actually did it. Each of those achievements seemed impossible until they became inevitable. Going beyond the moon will follow the same pattern. Right now, in 2026, it seems impossibly difficult. The barriers appear insurmountable. But teams around the world are chipping away at those barriers, solving one problem at a time, testing one system after another, learning from each failure and building on each success. In 10 years, or 20, or 30, we'll look back at this moment and recognize it as the beginning of something extraordinary. The transformation of humanity from a single planet species to a civilization that spans worlds. When that first crew lands on Mars, when human footprints press into red Martian soil for the first time, it won't mean that we've solved all the challenges. It will mean that we've learned to manage them, to accept the risks, and to move forward anyway. Those astronauts will still face radiation exposure, physical degradation, psychological isolation, and life support challenges. But they'll go anyway, because exploration has always required courage, because discovery has always demanded sacrifice, and because the human spirit has never been content to remain confined within known boundaries. The universe is vast, ancient, and filled with mysteries we can barely imagine. It doesn't care whether we explore it or not. The stars will continue burning whether or not we visit them. Planets will orbit their suns whether or not we land on them. The cosmos is indifferent to our existence. But we are not indifferent to the cosmos. We look up at the night sky and feel something stirring inside us, a yearning to know, to understand, to reach beyond our grasp. That yearning is what makes us human. It's what drove us down from the trees, across the savannas, over the mountains, and across the oceans. And now it's calling us to the stars. What's really stopping humans from going beyond the moon? Nothing that can't be overcome with time, ingenuity, courage, and determination. The barriers are real, they're formidable, and they'll test us in ways we've never been tested before. But they're not walls, they're challenges, and challenges are meant to be conquered. The question isn't whether we can go beyond the moon, the question is whether we will, whether we'll commit the resources, sustain the effort, accept the risks, and embrace the vision of humanity as a spacefaring civilization. That choice is ours to make. The universe is waiting. The journey is just beginning. Subscribe to the channel so you don't miss the next videos about space exploration. And if you were fascinated by the challenges we'll face going beyond the moon, you definitely need to watch the video on the screen. Why the first humans on Mars will be trapped there forever. In this video, we explore the disturbing reality that getting to Mars might be the easy part. But what about coming back? That's a completely different story.